what do we have to have? We're going to write a function as a series.
A over the sum of 1 minus r.
A over 1 minus r. That's the only thing we can do to write a function as a series. Why? Because a over 1 minus r equals?
The sum for a series.
Which series?
Geometric.
Geometric series, which is, the terms are? AR to the n. So this is all we have to go on now if we want to write a function as a series. So I've got this 10x times ln of 1 plus 2x. I need something that's like a over 1 minus r, which is not apparent, right? So we got fx equals 10x times natural log of 1 plus 2x. I need this. How am I going to get that?
Can we differentiate?
What do you want to differentiate? 10x, the whole function f? You're going to get, it's going to be product rule.
Just the ln.
Okay, if you differentiate the whole thing, you're going to get product rule. You're going to have two terms added together, which won't match that. So, what is the alternative? Integrate is, no, worse, okay? All right, so we see it, just the derivative of natural log would look like this, all right? So if I did, and so is that going to get, so before we get too far into it, is that going to be a viable way to do this? So let's do it. Derivative.
How are you splitting the function?
What's that?
How are you going to split the function?
So first of all, let's just do this. It's gonna be, what is it going to be? 2 over?
1 plus 2x.
So does that match this? Does that form match this form? No, absolutely it does. Of course it does. A equals 2 and r equals negative 2x. Okay? It matches perfectly. It matches perfectly. A equals 2, r equals negative 2x. Okay, so now the question is, we've got our function is 10x times natural log. So is this gonna be helpful? If I find a series for this, 2 over 1 plus 2x, then what? Then I can do the antiderivative, and I have the series for natural log of 1 plus 2x. Is that going to be helpful? Why?
Each term is multiplied by 10x.
Yeah. Yeah, so basically if I can rewrite this thing right here as a series, we talked about this principle yesterday, right, as a series, then what would the f of x be? What would f of x be if we can write natural log as a series?
10x times the series.
10x times the series, right? So our function is 10x times, because when we write this as a series, we're writing something equivalent to natural log of 1 plus 2x. It's equal to it. The series will be equal to that. So we can substitute, it's like we can substitute in the series that we find into this f of x, and then simplify it by just taking 10x times the series. And that'll be f of x. Does that make sense?
So, but that's not intuitive. That's like
We talked about it, I mean, kind of intuitive. What do you mean it's not intuitive?
I mean, it makes sense that we can separate it like this. We didn't talk about that yesterday.
Yeah, we did.
Did we?
Yeah. I said that we had x over, remember we had x over something. I said, look, you could do 1 over this, and then later multiply by x.
Oh, I didn't make the connection.
Yeah.
It's the same thing.
It's the same thing.
It's
the same thing.
Cool. Okay.
So this is where we actually need that principle. We actually need that principle here to do that. Okay, so we're going to write out what 2 over 1 plus 2x is. And that's going to be sum n equals 0 to infinity of 2 times negative 2x to the n. And we want to write out the terms. Well, first of all, let's rewrite that in an easier form. It's going to be 2 times so this is negative 1 to the n and 2 to the n. Okay, so we have 2 to the n. And we have negative 1 to the n. And then we have x to the n. So we can combine these and it'd be 2 to the n plus 1. So you get 2 to the n plus 1, negative 1 to the n, and x to the n. What's up? Okay, so let's write out, like I recommended yesterday, let's write out like maybe 4 or 5 terms. So when n equals 0, we're going to get 2x, no, 2. And then n equals 1, we're going to get 2 squared, or not, minus 2 squared x. And then when n equals 2, we're going to get plus 2 cubed x squared, and then minus 2 to the 4th x cubed plus 2 to the 5th dot dot dot. Did I write out those terms correctly? Check my work. I don't want to dig a hole for myself, so if you see a mistake at the beginning here, please speak up. Do we like it so far?
Do you have to factor it the way you do it?
Well, I recommend it. I try to do it the easiest way.
Can you just leave it like that?
Which way?
Like the upper, like, without having
Well, I foresee that we're going to be taking the antiderivative of this. And the form I have it in is going to be the easiest for taking the antiderivative. So that's why I'm doing this. I'm getting that x down to its bare bones. I just want x. I don't want negative 2x to the n. I want x to the n, because that antiderivative will be a lot easier. Or be less of an obstacle. So you could work the whole thing this way. I think this is easier. Okay, are we good? Do we agree with those terms? All right, so this is what our 2 over 1 plus 2x is. And now what are we going to do? No, we want to multiply 10x times natural log. This is the derivative of natural log.
Oh.
This is still the derivative. This is 1 plus 2x. We don't want to multiply 10x times this. We want to multiply 10x times this. Do you see? So we do antiderivative now. So antiderivative. And I want to do it also. We know antiderivative of 2 over 1 plus 2x is ln of 1 plus 2x. Antiderivative of this is going to be, well, 2n plus 1, negative 1 to the n. That all just stays the same because it does not do with x. And then what do we get? X to the
N
plus 1 over n plus 1. And now we're going to do this term by term as well. 2x minus 2 squared x over 2 plus 2 cubed x cubed over 3 minus 2 to the 4th x to the 4th over 4, etc. Now I just want to make sure my index is right. So let's try n equals 0. So if I start with n equals 0, do I get 2x? That's what we're asking. So if n equals 0, I'm going to get 2 times 1 times x. So I think n equals 0, and what I found here does give me 2x. And then I'm going to try n equals 1. And I'm going to get 2 squared times negative 1 times x squared over 2.
Cool.
Exactly right, right? And then let's just do one more. N equals 2 should give me this right here. 2 cubed, negative 1 squared is positive 1, x cubed over 3. There it is. So this is right, as long as I'm just going to start this with 0. What's that?
What about the 10x?
Not done. Yeah, we're not done. Okay, so what do we have? We have the function natural log of 1 plus 2x equals this series right here. So this is equal to this. So therefore f of x, if f of x is 10x times natural log of 1 plus 2x, then f of x is also 10x times what?
The series.
That series. Because that series is natural log function. Wow, I'm having a tough time making signals today. Better? Okay. Okay, so now we're gonna have a 10 in there, and then what's gonna happen to our power of x on every term? Instead of x to the n plus 1, we'll have not x squared. What does x to the n plus 1 mean? What does x to the n plus 1? What does it mean? That's not what it means. That's not what it means. What does x to the n plus 1 mean?
X multiplied by itself n times.
X multiplied by itself n plus 1 times. Now we're going to multiply that by x. So what will that be?
X to the n
N plus 2.
Right. You're going to multiply it together n plus 2 times now because you have one more x. So we're going to have the sum 0 to infinity of, we'll do the alternating part first, times 10, 2 to the n plus 1, times x to the n plus 2. We got one more x that we're multiplying by. This is multiplying many x's together. Now we're going to multiply in one more, which is n plus 2.
Is that 10 times 2?
Should there be an X?
So negative 1 to the n times 10 times 2 to the n plus 1 times x to the n plus 2 all over n plus 1. Okay, now we have to shift because they want it n being 0 being x to the nth power. So we got it, but now we have to do this. We have to shift to answer the question, to put in the answer blanks. Okay, so how do we do that? Let's see.
We add 1 to n.
Start from n equals
Yeah.
So we have to start from n equals, so the very first, so the first power of x that we get is x squared, right? So that would be, if we have x to the n, then we'd be starting at n equals 2. Do you see it? So I'm going to, I'll leave that written down. I'm going to give myself some room here. So basically, if we need this to match this, then the first term that we'll have is going to be n equals 2. Because we need the n here, whatever n is, has to be the power of x. The first power of x that we get when n equals 0, the first one we get is x squared. That means if we're writing it as x to the n, the first n value we would have would be n equals 2. Is that okay? So then this would still be negative 1 to the n. That's fine. And we'll still have 10. Now, when we, erase that. Okay, so when we have our first term, n equals 0 will give us 2 to the first. So we need n equals 2 to give us 2 to the first. How do we do that? So when n equals 2, that's when we get the x squared term, and that's when we should get 2 to the first. So we want 2 to the n minus 1. Okay, and then when we got that x squared term, it was over 1. So now we got the x squared term, it needs to be over 1. So if n equals 2, that would be n minus 1. So ours is going to start with C2. When n equals 2, that's our first one. So our C2 is going to be all of this stuff with 2 plugged in. So that's our Cn. That's our Cn right there. Okay? Okay, so with n equals 2, it's going to be positive 1 times 10 times 2 to the 1 over 1. So what is that? So negative 1 squared is just 1, so we're going to have 10 times
8.
times 2, that's it. It'll be 20. Okay, C3. C3 is when n equals 3. So it'd be negative 1, or negative 10, times 4 over 2. And then when c equals 4, we'll have positive 1 times 10 times 2 cubed, or 8, divided by 3. What about C naught and C1? 0, right? So we don't have those terms. We don't have n equals 0 and n equals 1. The first term we get, it corresponds to n equals 2, so these have to be 0. Okay, got it. Okay, so there was lots going on there. Did I lose you?
So when you multiply it into 10x, I'm not tracking that. So you have the 10x times
The series that
the
we found,
series.
right? The series.
So how did that
here's
end
the
up?
series. So this is a sum of things, right?
Yeah.
So the 10x is just going to be multiplied by every one of those. So you're going to have times 10. That's the 10.
Well, why is you still negative 1 then? Don't you multiply the negative 1 by 10 too?
Okay. Okay. What you have is 10 times ABC plus DEF plus GHI. Okay? This is not, so when you multiply this 10 in, it's not 10A times 10B times 10C plus 10B times 10E times 10F. What is it? It's 10ABC plus 10DEF
Okay, yeah. The ends are
plus 10 GHI. You see?
Yeah.
So you distribute 110 to each term, not to every factor of each term. Okay? So is that clear up the 10?
Yeah.
And then you're going to multiply x in, so that's going to combine with your x to n plus 1. You're just going to have one more x, so x to n plus 2. Then we had, in order to answer the way Weber set it up, we had to have our n match up with n equals 2. We have to get the power of x to be the same as n, right? And so if we look at our first power of x is x squared. that means our first n is going to be 2 when it's x to the n. And then we figured out how do you need to adjust. And so basically, this is called shifting the index. And so since we added 2 to n, we basically subtract 2 from every n. So subtracted 2, we got n minus 1. Subtracted 2, we got n. Subtracted 2, we got n minus 1. That's what I was using.
So what are we trying to plug in to find the values of? So we're plugging values of Cn and x to the n to find the values of what?
They want the CNs, right? They want the first. They want C1, C0, C1. If we wrote it this way, if we wrote it as an expression times x to the n, where your index is the same as your power. So we want these, everything else but x to the n is what they want for 0, 1, 2, 3, and 4. Right? So that's why I put the circle in there.
That makes sense.
So that's all our CN term, and so they want it for n equals 0, 1, 2, 3, and 4. But there are no terms for, if it's written this way, there is no terms for n equals 0 and n equals 1. So those would be 0. The first term we get is an x squared term, which is C2. So I plug 2 in for n, and that gives me my C2. Ask me again. See, what is this here? What is this up here? This is C naught x to the 0 plus C1 x to the first plus C2 x squared, etc. They're asking for just these coefficients. So that, for us, in this problem, that's this whole thing is the coefficient.
So then we're trying to find the value of n that makes that equal to 2.
So now, so go back to what is your original question? Is your original question, how did I get this expression from this one?
No,
Or how am I getting these numbers? Or
it's
something else?
What you, yeah, it's kind of like, why are you getting those numbers? Because what are you trying to, yeah, why are you getting those numbers? Why are you,
Okay, so do you understand how we got this?
yes.
So this does not match the form of this in order to put these answers in. Because the form of this series is that the exponent of x is the same as the index. All right? Here, the exponent of x is not the same as the index. It's 2 greater. So the first term I get here is with an x squared. That means if I'm going to write it in this form, that means the first n value I'm going to have is n equals 2. So when n equals 2, then I can have x to the n, and I'll get that first term x squared. Just like here, when n equals 0, I get x squared. I need the index to match the exponent in order to write it in this form. See, the index has to match the exponent, n and n. But mine doesn't.
Okay.
So the first term I get is an x squared term. So thinking about this, then that means my first n value that's going to be non-zero is going to be n equals 2. So when n equals 2, then I'll have x squared. And so that's how I started. I started with n equals 2, x squared. Now all the rest is Cn, and now I've got to adjust. Because I just adjusted that n, I've got to adjust all of that. So I get the right coefficient when I have x squared, which adjusts all that. So when n equals 0, I said that I have 10 times 2 over 1. So then I had to make this n minus 1 and this n minus 1 so that I get 10 times 2 over 1 when n equals 2 now. But kind of just as a quick easy rule, if I increase the index by 2, then I just have to reduce all my n vectors by 2. So I increase n by 2. That means make this n plus 1 less 2, n plus 1 less 2, and n plus 2 less 2. And that will give me the same terms as I had before.
So it's -1 also increased by.
Yeah, but that's the same thing, right? So when you, because it's -1 to
N plus n
right.
minus.
So I can do n minus 2, but that's the same as -1 to the n. Because it's just the evens will be positive and the odds will be negative.
Yes.
Now, if you only shifted by 1, then that matters. If you shift the index by 1, then now you're changing the sign of all of them. If you shift by 2, you keep the same signs. Okay, other questions on this example? Lots of important ideas. Then they want the radius of convergence, so we'd have to do our limit, our ratio test.
So what if you leave this? What if you just do it as C with a sum of n plus 2? Then equals what you have on the bottom.
We can just do the one that we have in the end.
But you would,
What are you talking about?
Trying to do
Changing
the
the C sub
Once
3.8,
instead
you do
of
that.
taking subtracting 2, just take it the way it is. Just take C sub n plus 2. Then you just use that.
you just use that. I don't understand.
You get it.
Yeah, I get it. So are you trying to say like if we just take the ratio test of the
Once instead of going there, instead of finding that out there, we just use like.
But the form of the answer, in order to get the Webwork problem right, you have to have it in this form, where the n matches the exponent. That's why I had to do all this. In order to put these answers in, whatever n is has to be the exponent of x. That's why I did this shift. Because here, n is not the exponent of x. X is 2 greater. The exponent of x is 2 greater than n.
so it's okay to take the ratio test when n is equal to 2. That's
Yeah, because the ratio, it's the limit as n approaches infinity. It's like n gets very large. So it doesn't matter if we start at 2 or 0 or 100.
well, we can.
The ratio test is for n very, 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 very large.
Yeah, I understand that. So we can take the ratio test with it in that form, right?
Sure.
Okay.
Okay. More questions? All right, one more day of these, and then we'll move on to something else. Okay, so Taylor and Maclaurin series. Okay, so relatively few functions exist that are of this form, a over 1 minus r, right? So in order to write a function as a series, in what we've done so far, it had to be a over 1 minus r. Well, it's very specific, very restrictive. Your problems have to be totally rigged, right? So this is a minuscule fraction of all functions. Ones that look like this or related by differentiation. So a Taylor and Maclaurin series allows for writing any function as an equivalent power series.
That's a big thing.
Yeah.
Memorize them?
What's that?
Do you have to memorize them?
You have to memorize what?
The rules. You know, like sine, cosine, whatever the function is. Because that's
I'm more interested in is if you can derive them. Yeah. I'm not very interested in memorization. I mean, fortunately that's necessary in a lot of little things, but I'm always more interested in your ability to understand rather than memorize. Okay, so a Taylor series centered about x equals a is a power series of this form right here. And this first thing here in the numerator is the nth derivative. So that's not raising it to the nth power. That's the nth derivative of f, and then with a plugged in or evaluated at a. Okay, so we see this and we think what? Write it down. We see this and we think what?
I think, how did this guy figure that out?
We're just practicing series here. So what is the zeroth derivative?
I was just gonna ask. It's just f, right?
What is the zeroth derivative? Is it just f?
It's just one.
Means you haven't taken any derivatives yet.
That's just f.
Is it 1 or is it f? F. You haven't taken any derivative. Okay. Zeroth derivative, just you haven't taken the derivative. It's just f.
What's 0 factorial?
0 factorial is 1 by definition.
When you get into higher derivatives, how do you write it? Is that
Roman numerals.
Roman numerals?
Okay, so you should have this. Is this what you had?
That's like past 3 you do.
What's that?
Like past the third derivative, you would put like that Roman 4.
Yeah, Roman numerals. Or you could just keep putting 6 if you wanted. Because rarely do we do 4th, 5th, 6th derivative explicitly. So, okay, make sense? That's equivalent to that series. Okay, so then a Maclaurin series is just a Taylor series, especially when your center, your A value is 0. So now I want you, for your notes, you're going to write Maclaurin series, and you're going to write out the sum form and the expanded sum. So it's the same thing as a Taylor series, but specifically when you're centered about 0. Okay, and you should make all appropriate simplifications. So write out the Maclaurin series. Write it both ways. Write it as a sum and as expanded terms. Rather than just copying it down, how do you do it? Okay.
these guys contemporaries?
I don't know.
It seems like a lot to take credit for, just one case.
Okay, so you should have this. Is that what you had? Okay, so I'll write the Maclaurin series for y equals e to the x. So what does that entail? That entails all the derivatives of e to the x. What are the derivatives of e to the x? Times x.
Times x prime, which is 1.
Okay. Yeah. So all the derivatives are e to the x, but then we need, for Maclaurin series, then we need the derivatives evaluated at 0. Which is what? 1, right? So all these derivatives for the Maclaurin series for e to the x evaluated at 0 are just 1. So we can write it down.
So the only thing that's changing is the bottom, is the denominator.
No, that's not true. Okay, so what's the first term?
E to the 1.
First term is e to the 1.
No. E to the 1. 0.
And I'm plugging 1 into anything.
It's one.
It's 1, right? It's 1 over 1. Second term, 1 plus x. All the derivatives are what? All the derivatives evaluated at 0 are 1.
1.
All the derivatives are e to the x. We evaluated them 0, so all the derivatives evaluated at 0 are 1. 1, 1, 1, 1. So we have very little left here. So the first term is going to be 1 plus,
So 1 times 1.
okay, which is
0.
1 factorial, guys?
1.
1. Okay, so it's 1 over 1 times x.
X.
Then 1 over
2.
2 times squared. 1 over, just leave it as factorial, okay? Leave it as factorial.
This is cool.
So then, what is the radius of convergence for this? So can we do the ratio test fast? We get x over n plus 1.
It's over.
X over n plus 1. We want the limit as that. As n. So for what values of x is this thing less than 1?
When x is less than 1.
So only when x is less than 1. For what, I'm asking for what values of x is this limit less than 1?
For all.
All x, right? All x. Why? Because that thing, this is going to go to 0 no matter what x value you pick. No matter what x value you pick, that will get a lot bigger. A lot bigger, right? Because it will just get infinitely big. So this is, so it's true for all x. So let's take a look at it. So our function e to the x So now we don't want this anymore. Okay, so what do we say? 1 plus?
S.
Let's just do that much. Good approximation? Well, it's good at 0, right? So we say centered about, it's based on all the derivatives at 0, right? So at 0, this is, when you get, if we were to zoom in right there, it'd be a decent approximation, right? But it's supposed to converge for all x, right? So let's do plus x. This is supposed to be over 2, right?
That's over 2 by 3. Oh, nice. Already it's big.
So now it's pretty good from -1 to 1 or 2. Do one more here. So look at that. So it's kind of hard to see, but so our e to the x goes is asymptotic with this x-axis out here. So when you have these first, what is this, 8 terms, 7 terms, it's a pretty good approximation all the way from -3 to 4-ish. So you can see the blue here. You see e to the x then being asymptotic, and our approximation going back up. But say here from about -3 to 4 or 5, it's hovering pretty well. And so the more terms you add, the more it will be close to the function for a larger and larger interval. And if you could add all infinitely many terms, it would be exactly e to the x everywhere for all x values. Okay, and so then this is called a Taylor polynomial. So when you do an approximate by just taking a partial sum, it's called a Taylor polynomial. So this would be degree 6. This would be a degree 6 Taylor polynomial, which is an approximation to the Taylor series, right? And the more terms you add, the better the approximation to the series.
So it has nothing to do with the number of terms, it's just the degree of the polynomial.
Usually call it out by the degree. Yeah. Usually call out the polynomials by the degree. Okay. So then, now that we have e to the x as a series, we can use it just like we saw in the example that we did from the homework, where it was like 10x times the series for natural log. We can do all kinds of variations. We can find series for variations on e to the x. So first of all, we could do something like we could estimate, say, estimate e to the 4th. so can you do this? So can you estimate, first of all, use the series to estimate e to the fourth, and then find series for these variations on e to the x, e to the minus 3x, e to the x over x, and e to the function e to the x minus 1 minus x. So let's do these for the sheet. We can work on this together.
From each term in the series.
But it's not, it's like you're trying to distribute this.
No, I'm just saying, so I know what e to the x is,
Okay.
and so then.
So now I want e to the x minus 1 minus x. So I got this series. What will I get?
X plus x minus 1 minus x plus x squared. No.
You're confused. I've got a sum of a bunch of terms. 1 plus x squared, blah, 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 blah. Now I'm going to subtract 1, and I'm going to subtract x from that.
Oh, so it just removes the first two.
Right.
That's so cool.
So basically I'm saying take this, which is our e to the x, minus 1 minus x. What do you get?
Every term except the first.
Yeah, you get the rest of the terms. You got to take away the 1 and take away the x. So that's a very rigged function, right? If I said e to the x minus 2 minus x squared, that wouldn't work, right? This is totally rigged because the first term is 1 and the second term is x.
Yeah.
Okay, so now we want to write that. How do we write that in summation notation? So now we don't want the first two terms. So what can we do?
We just start at 2.
Yeah, start at 2. Okay, and now we want to write it starting at 0. How can we do that? So what did I just do? I just subtracted 2 from the index, therefore,
Add 2.
and then check it, okay? Make sure it's right. So
Which will tell us what index you want.
no, conventionally, starting at n equals 0 is the convention,
Okay.
or 1, okay? But normally now that we're into this point, most series will start with 0. So now check it. So when you plug in, when you plug in 0, what do you get? You get x squared over
2.
factorial, and that's our first term. There it is. When n equals 1, you get x cubed over, there it is. So when you do a shift of index, all you have to do is check it. So now you look at this, you see this, you think what? Figure out what the terms are. Do they match the ones that you had originally? And they do. So this right here is the function e to the x minus 1 minus x as a series.
So for the negative exponent one, can we just apply a constant to each of the terms? Like if I split it into e to the negative 3, no.
If e to the x is this, then what's e to the minus 3x? Or how would you get it?
It would be 1 plus minus 3x or 1 minus 3x. And then
I'm not sure the first term is going to be. Oh, okay. Right. Right, yeah. So anywhere there's an x, now you have negative 3x. Anywhere there's an x, so e to the negative 3x will just be wherever there's an x, I have a negative 3x. So okay, and then if we wanted to bring out the alternating part separately, we could write it as negative 3 to the n, or negative 1 to the n times 3 to the n. So that's the series for e to the minus 3x. Okay, any questions? So we gotta kind of move here so we can get to the homework stuff. Can we go on? Is there a question? Yeah.
How do you do the unity x1 by x?
So it's just like what we did in the example at the beginning of class. You've got a series, and now you've got the equivalent series, and now you get divided by x. So it's just go review the very first example we did in the homework. It's going to be the same principle as that. Okay, so I actually want to do cosine here. All right, so we're going to write Maclaurin series for cosine 3x. So there's our general formula of Maclaurin series. So what's really the biggest part of finding this? It's finding all these derivatives evaluated at 0. N factorial, x to the n, piece of cake. So really the bulk of doing this is figuring out what those derivatives are. So I recommend setting up a table. And just find enough terms so that you have established the pattern, okay? So, what's the 0th derivative of the function? Cosine of 3x. Yeah, it's just cosine of 3x. I didn't leave enough room here. Okay. So what is this is saying if n equals 1, we want the first derivative of cosine 3x. Negative 3 sine 3x. Okay? And so this is now saying what's the second derivative of that? So negative 3 squared cosine 3x. And then what's the third derivative, or the derivative of that? Well, we're going to get 3 cubed sine 3x. Okay, etc. So derivative is going to be 3 to the 4th cosine 3x. Negative 3 to the 5th sine 3x. Negative 3 to the 6th cosine 3x. And then 3 to the 7th cosine 3x, sine 3x. Make sense so far? So those are all the derivatives, the first 7 derivatives. But then we need, for the Maclaurin series, we need those evaluated at 0. Okay, so at 0, cosine of 3x when x equals 0. Okay, that's going to be 1. This is going to be 0. Okay, and then we're going to get negative 3 squared. Then we're going to get 0. Then we're going to get 3 to the 4th. We're going to get 0. Then we're going to get negative 3 to the 6th. 0. Okay, so then cosine of 3x equals? Okay, it's going to be 1 over, so when n equals 0, we're going to have our derivative is 1. It's going to be 1 over 1, x to the 0, so you're going to have 1. And then it's going to be plus 0, because that for n equals 1, the derivative is 0. And then when n equals 2, we're going to have negative, so it's going to be minus 3 squared over 2 factorial x squared. Okay, and then plus 0. It's right. I'm going to start over and make more room. So it's right. Is that what we did? Next one, b plus 0. And then plus 3 to the 4th, x to the 4th over plus 0 minus 3 to the 6th, x to the 6th over, and so on. Okay, so can we write a formula for this?
You mean like in series notation?
Yeah, so now we want to write it in series notation. So the reason I kept these as 3 squared, 3 cubed, etc.
But how do we get this weird sign pattern?
Okay, so yeah, so here's the deal. What we've got is every other term is 0. So in order to do that, we have to so this came from our n values being 0, 1, 2, 3, 4, 5, 6, 7, like that. But now we're going to need to we saw this before, we're going to need to re-index it so that this is 0, and then this is 1, and this is 2, and this is 3. So this is going to be our new n, is going to be according to the non-zero terms. Okay, so in web work, if they said find the first, if it was cn x to the n, and they said find the first coefficients, well, you have it, right? So your coefficients would just be 1, 0, 3 squared over 2 factorial, 0, 3 to the 4th over 4 factorial, right? Like what we saw earlier in the example. So if we wanted to write this as cn x to the n, then you can just, you're done, you got it, because your 0 matches, your n matches your exponent of x, and so then every other one would be a 0. But if we want to write this Maclaurin series for cosine 3x as a series, not just in the general form, then we need to re-index it so that we don't have those zeros in there. So now the red is the new n. And so I guess it'd be easiest to come out here to one of these toward the end, like this, when n is 2 or n is 3. So first of all, we have alternating, so it's going to be -1,
to the n. Does that give the right sign, or do we need n plus 1?
So when n equals 0 and 2, we should have positive, and when n equals 1 and 3, it should be negative. Is that what we have?
Yeah.
Yeah, so negative 1 to the n works.
And now we're going to look at, say, what is our formula? Say here's n equals 3. What is our formula? 3 to the what?
2n.
2n, right? That's twice as much as that. 3 to the 2n times x to the 2n over 2n factorial. Did you catch it?
So now when n goes 1, 2, 3, 4, it should be 1, 2, 0, 0, 1, 2, 3. We'll give you that expression, will give you those, the non-zero terms this way. But if you don't want to generate, if you're not generating the actual series notation, and you just want the coefficients according to this form, then it would be, then your coefficients have a 0. Every odd term has a 0 coefficient.
Okay, questions? Does it make sense?
So where do we go from here? Like why do we want functions as series?
Because polynomials, so it's basically a way of writing any function as a polynomial. But to get it exactly right, you need all of the terms. But if you took, if you did 10 or 20 terms, usually that would be very, very, very close. Okay? So polynomials are they're more easy to work with, like integrating and differentiating. They're very simple to do that. So they're just easier functions to work with.
Okay, you got to do one more. So you're ready for the homework? So let's do, I thought I had another slide. There it is. So I'm going to do the Taylor series for ln of 2x about x equals 3. So remember, Maclaurin series are centered at 0. Taylor series are centered at any value. So here's what it would be. So the Taylor series about x equals 3. I had this wrong. So these should be 3's. Okay, so here we go. So I'm going to go fast for time's sake. Try to track with me. So the 0th derivative is 2 times 1 over x, right? No.
No, just the function.
Yeah. It's the next one. ln of 2x. Okay, and then if we want to find the function at 3, it'd be ln of 6, or ln of 2 times 3. Okay, first derivative. 2 times 1 over 2x. At that value would be 2 times 1 over 2 times 3. Next derivative would be
2 times negative 1 over 2x squared.
X
I think that we should simplify this one.
Just gotta be one.
Yeah, it can be 1 over x.
Oh yeah, natural log of cx is just 1 over x, right? Any constant?
Yeah.
Okay, cool.
All right, and so then next derivative is going to be negative.
Negative 1 over x.
Okay, so this will be negative 1 over 3 squared. And then we'll have positive 2 times 1 over x cubed. Right?
Is it negative or
Oh, yeah, you're right.
So that's 2 times 1 over 3 cubed. And then we're going to have 3 times 2. Negative 3 times 2 times 1 over x to the 4th. Or negative 3 times 2 times 1 over 3 to the 4th. And then positive 4 times 3 times 2 times 1 over x to the 5th. And what is happening here? 2, 3 times 2, 4 times 3 times 2. What are we building? Factorial. So this is 4 factorial times 1 over x to the 5th. And then we have negative 5 factorial,
This is amazing.
1 over x to the 6th. So negative 5 factorial, 1 over x to the 6th. I think that's enough to establish the pattern.
I have a quick question for the factorial.
Yeah.
If it's negative 5 factorial, would it be negative 5?
No, it's the opposite of 5 factorial.
Oh, okay. So negative 6.
The negative is just out in front here. Okay? So let's write out the terms. So we got, so notice that this, the first term, ln of 6, doesn't follow the pattern of the rest. Do you see that there's a pattern here forming that this isn't part of? So we need to have this separately outside of the summation notation, right? Because this isn't part of this pattern. So we're going to start off with ln of 6, and we're going to say plus, starting at n equals 1, f this little thing.
You did that because the 0th term is not part of the pattern.
Yeah, this is not in this pattern. So we won't be able to write, if we're going to write one pattern for all of it, that can't be part of it. All right, so let's write out the terms. So ln of 6, and then when n equals 1, what do we get? 1/3 over n factorial, x minus 3 to the n. Plus, or minus, sorry. Negative 1 is 1 over 3 squared, n factorial, x minus 3 to the n. Sorry, not n. This is 1 now. So squared.
So on the bottom we have 1.
Next one's going to be 1 over. So now that we have this factorial coming up here. So we got plus. What is this? 2 times 1 over
2 over 3 thirds.
cubed. Dang it. Sorry, it's not ends. You don't have any ends. We're doing it for each end. This is 1, 2, 3 factorial, x minus 3 cubed. That's going to be minus. This is our 3 times 2, so this is our 3 factorial. And this was actually 2 factorial back here. 3 factorial, 1 over 3 to the 4th, over 4 factorial, x minus 3 to the 4th. Okay, so if we want to write what the formula is, it's going to be ln of 6 plus, we're alternating, starting with n equals 1. And we want it to be positive first, so we want like n plus 1, okay? So that when the ends are odd, we get positives. And when the ends are even, we get negative. And then we're going to have, so this is n equals 1, 2, 3, 4. So let's look here at the 4th term. We have this factorial that's what? 1 less than our value of n. So n minus 1 factorial. But then that's over n factorial, right? From just the general formula. And then 1 over 3 to the, that's just the, whatever the index is, times, yeah. So the only thing left to do would be, we could simplify this. N minus 1 factorial over n,
It's just gonna be
what are you going to get from that?
n.
N in the denominator, right? So that can simplify to just n down here. So last time, and we'll go ln of 6. Sorry guys, take it way over here. Ln of 6 plus sum n equals 1 to n, or to infinity, negative 1 to the n plus 1. So x minus 3 to the n over n 3 to the n. So I wish I had time to show you the graphs, but I could show you the graph of ln 2x, and then we could start writing some of these terms on the graph, and see that at 3, it would be exactly correct, and then it would, it would do something like this. And then the more terms that you added, the more that the Taylor polynomial would conform to natural log of 2x. But centered at x equals 3 means we get it perfectly right at x equals 3. The more terms that you include, the more that graph would conform to natural log.